Hello and welcome to the April 2021 session of the Ivado webinars. My name is Fabien Perrineau. I am an Industrial Partnership Advisor at Ivado, and today my colleague Lilia Gemai and I will be your hosts and moderators. So before we start, a couple of housekeeping rules. The microphones and cameras of all attendees will be turned off for the whole duration of the webinar. However, should you have any questions to ask the speaker, you can use the Q&A button to type in your questions, or use the chat for those of you following us on YouTube Live. So questions will be addressed during the Q&A session, which will take place right after the presentation. And this webinar will be recorded and then made available afterwards on YouTube. Today's topic will focus on autonomous robots. You probably already know what is a drone or a self-driving car. These robots are getting more and more present in everyday life as they are becoming more and more sophisticated. They can act as enabling technology for many kinds of applications, such as search and rescue, inspection, or error mapping. Still, there are challenges in maintaining swarms of these robots. And so today we will see an overview of current solutions in programming these robots in a safe and manageable way, illustrated with practical examples in the areas of disaster response and space exploration. So to talk about this, today we have the pleasure to welcome Giovanni Bertrami. Giovanni Bertrami is a professor at Polytechnique Montréal. He has an international reputation in the field of intelligent embedded systems and robotics. He has published more than 100 articles in high-level journals and conferences, and his laboratory has developed the best programming language for swarm robotics. His presentation, How Do You Program 1,000 Robots?, was given dozens of times around the world, and he has been a principal investigator in more than 20 projects in the fields of robotics and embedded systems. His laboratory has been involved in several field missions, including this European Space Agency Pangea X analog campaign with a swarm of drones, several experiments for search and rescue, as well as the IGLUNA campaign for the lunar exploration with swarms of robots. Dr. Bertrami is also collaborating with the NASA on their underground robotic exploration. So without further ado, Giovanni, the floor is yours.
Thank you. Thank you for the nice introduction. So I'm going to share my screen so that you can see my presentation. And welcome everyone to this talk. Today, I want to give you an idea of what we need to do, what we have done, and what we still need to do in order to get swarms of robots to actually work in real life. So having us interact with swarms of robots in our daily lives. Before we go into swarm robotics, I would like to mention swarm intelligence. I could make an entire lecture about swarm intelligence, but it's important to know what this is. And usually when I introduce swarm intelligence, I show this video. This video is absolutely fascinating, in my opinion. These are fire ants. These ants, what they're doing, they are escaping from a flood. So they are working together. They are using their own bodies to make a raft, and this raft is capable of floating and taking the queen and the larvae to safety. This is extremely interesting because these ants know what to do. They have very tiny brains, and yet they might not have seen ever in their lives a flood, because floods might not be that frequent. But yet when this happens, they know what to do. They know how to collaborate to form this raft, and they don't die. It's not like some of the ants sacrifice themselves. This is the essence of swarm intelligence. Small brains, small local rules that only see what's around them. There's no global communication or global orchestrator, that they work together to accomplish something that would be impossible for a single organism. So there are many examples of swarm intelligence in the natural world. We have flocks of birds, we have schools of fish, we have swarms of bees, we have fire ants, like you see here, that they can form bridges to go and get food. So we have a lot of these examples. And what is interesting about natural swarm intelligence is that it has very useful properties for us, roboticists, that want to engineer these similar systems in the real world. First of all, these are extremely efficient. So if you have, you know that ants do not use a lot of energy. They need to eat very little, and yet with the little energy they use, they are capable of these feats. It's very robust. You can squash a bunch of ants, you can kill some fish, and yet the system still works. They are inherently parallel, meaning that the thinking of each of these organisms goes in parallel. We have also another example that is your own brain, because you have a lot of neurons working together to form your consciousness. So this is what is, it's inherently parallel, and it's extremely adaptable. You take the ants, you put them in a different location, they will still be able to find their food and to work and to act as a community. So how do we go from this natural swarm intelligence to artificial swarm intelligence? Well, what I'm working on is a combination of two fields. The field of collective robotics, where you have a bunch of robots working together, and the field of swarm intelligence, where we study natural swarm intelligence to understand how it works. And the intersection of these two fields is swarm robotics, and that's where we want to work. There are a few design principles that we need to follow in order to replicate what swarm intelligence is giving us, natural swarm intelligence. First of all, is what we call decentralized control, meaning that there's no leader. Everything is done by the single discrete elements of a swarm. So there's no central control. You've seen probably in videos that, or in movies that, oh, you kill the queen and everybody stops working. That is not true. In fact, in general, you have multiple queens. But the point is that there are no leaders, and there are no predefined roles. And some ants can work as foragers or as soldiers. And so they can change roles depending on what's needed by the environment. And this is the same for humans. And most importantly, the entire behavior is controlled by simple local interactions, meaning that organisms interact only with their neighbors and not with the entirety of the swarm. If we can engineer these systems, we have a lot of potential applications. We can do military demining, we can do construction, we can have robots working together to build, we can explore caves, we can monitor infrastructure, we can even do nanomedicine. If we have very tiny robots that are not particularly intelligent, but they can work together to do something more, they can eliminate cancer cells or something similar. We can also do disaster response or space exploration. So what we want to have is something that for the future, we have these swarms of robots performing all of these applications. And this is our vision of the future. So swarm systems that perform tasks that would be impossible for single robots. Now you see this is clearly Photoshop. This is not a real picture, but this should be something that looks familiar to some of you. In particular, we might think that we have seen already large swarms of drones. For example, this video from the Winter Olympics in South Korea, we had thousands of drones working together to form patterns in the sky. So is this a solved problem? Well, let's take a look at Intel's drone show and our design principles. First of all, decentralized control. No, not really. Intel's drone show is a centralized planner. So everything is decided in advance by a single computer that distributes the tasks to all the other robots. There's a ground station that controls everything. The robots do not necessarily have a particular sensing. They know their position thanks to GPS. And they act based on their script and nothing else. As in fact, they do have predefined roles. Every single robot has a specific role that it has to accomplish. And there are no local interactions. The robots do not talk to each other. They have GPS-based trajectories, so they know where they are and where they have to go, and they don't talk to each other. So we're still not quite at the point of a viable swarm system in real life. And that's why we are doing the research in this area. And today I would like to show you the sort of recipes that I think need to be implemented to get the swarms on in the real world. First of all, we have to consider that designing a swarm system is not necessarily simple. We have what we call the global to local problem. For you, some of you, it might be easy to determine the requirements, so what the swarm has to do. And the problem is that the swarm is not a single entity, but it's made by many discrete robots. So how do we translate these requirements to an actual implementation on the robots? And we had long discussions on this in the lab, and my former postdoc, Carlo Pinciroli, who's now professor at WPI, said, let's make a new programming language. At the beginning, I wasn't too sold in the idea, but I got convinced, because swarms are very special systems. We won't go into the details today of how this programming language works, but the idea is that we need a way to tell the swarms what to do. And we have several options to do so. So how do we program a swarm? We can tell each robot what to do. And this is what people normally do with the robotics. The problem is that this doesn't scale. If you have thousands and thousands of robots and they have to adapt to the environment or to whatever is changing, writing the code in this way, it's basically impossible. So we can tell the swarm what to do. But the problem is, again, transforming what the swarm has to do into single robots. And even if we have a system where we assume that we can transform this description into behavior for each robot, one of the problems is that we lose completely track of special robots. If you have robots that one robot has an arm and one robot can fly, one robot has wheels, how can we differentiate if we're telling the entire swarm what to do? So in our language, we managed to put all these things together. And so we can tell each robot what to do, as well as what the swarm has to do. On top of this, we have to manage the neighbors. So remember the simple local interactions, we need to manage what the communication is with our neighbors. And this is implemented directly into the language. And extremely important, we need to be able to establish global consensus. What is global consensus? When you have many robots that have to act together, they have to agree on what needs to be done. And this is one of the standard things we have to consider for even in our daily life. We go to meetings to agree on what needs to be done. We have project management to get everybody on the same page to do things. So establishing a global consensus, having the robots agree on something, it's paramount. On top of this, we realized that we needed this language to be predictable and support what we call heterogeneous swarms, so swarms that are very different from each other. So in the end, we designed this new programming language. There are many programming languages. There are every day, probably there are tens that they are created. I don't know. But our programming language has a twist in the sense that we don't want to reprogram everything. We don't want to reinvent the wheel. So we made the language that is used just for the coordination between the robots. How does it work? Imagine that you have an operator and a bunch of different robots. Note that these robots are different. Some flying, some have an arm, and some are just wheeled robots with sensors. Note the presence of this operator. Some people told me a long time ago in reviews for papers that, we want our systems to be fully autonomous. We don't need an operator. And to this, I counteract with, I respond with saying, what is the purpose of a system that doesn't have any contact with an operator? Suppose we take a bunch of robots, we send them to Mars, and they never talk back to us. There's completely no point in sending them. They might be having fun there, but we're not getting any information. So even if it's just for monitoring, it's extremely important to have an operator communicate with the robot network. So the operator writes this sort of code and then distributes it on all the robots. Note that we have the peculiarity of our language is that it's a single code, and it's the same code that is distributed on all the robots, even if the robots are different. This is just like humans. We do different things despite the fact that we have the same DNA mostly. And even if you take a bunch of ants, they are mostly identical. They have very tiny differences, but so their code is the same, but they act differently. And this is because the code adapts to the environment and to their life. So with this particular language, we can assign tasks based on what the robots are capable of doing. So we can say, for example, flying robots have a certain task T3, or wheeled robots have a task T1, or other robots have a task T2. And this comes from the same script. Doesn't matter how many robots you have or how many different types you have. The idea is that you write your code and this code adapts to the swarm as it moves. Just to make you understand what we can do with this, I have a very, very simple example. This is the simplest example you can have of swarm behavior. These robots that you see here are tiny robots with, they're about the size of a dollar coin. And they can move by vibrating their legs, and we usually use them for experiments. The interesting thing about these robots is that they can communicate only with a range of about 7 centimeters. So they talk wirelessly with infrared sensors that they have underneath. They bounce the signal and they can talk to their neighbors. So it's perfect for studying swarm intelligence. Here, what you see is robots that have either they have a green LED or a red LED or a blinking LED. And this is the explanation of our programming model in a nutshell. We have robots that have one task, do the LED red. We have another set of robots that have the second task with green. And you can also have robots that have both tasks, green and red. And so they keep jumping from one task to the other. By combining these tasks, you can specify all kinds of behaviors, as we will see in some practical examples. Now, imagine now we have a programming model, we have a programming language, we know how to assign tasks to the robots. The only problem we have is that we're still missing this idea of global consensus. So to solve this issue, we got inspiration from the natural environment. And in particular, we looked at stigmergy. I don't expect any of you to know what stigmergy is, but stigmergy is what we call indirect environment-mediated communication. What it is having a bunch of insects talk to each other by changing the environment. Ants can drop pheromone, so a chemical that can be smelled by other ants and provide messages. Humans do this too. We put signs on the road. We change environment to leave messages. We make small piles of rock on the Alps or on the mountains to mark the path. Social insects do something very similar. So our take is that we create a sort of virtual environment where we can put values, can put variables that the robots can agree on. And these variables are automatically, this is embedded in our language, propagated across the swarm. So if you want to see an example, here you have extremely slowed down information propagation. So you can see how the robots, when the robot reads a new signal, this information can be distributed across the swarm, and the swarm can reach a sort of an agreement on this particular variable. And agreement is the key to get the robots to do things together. Now, when we designed this, we started agreeing on little variables. So they can agree on the temperature of a place. We can agree on what task I need to do, just the name of the task. But we know that robots have vision, robots have very complex sensors, we have artificial intelligence, and as many people might have told you, big data is the future. So robots need to share much more than tiny bits of information. And agreeing on large data is kind of complicated because you cannot replicate across the entire swarm. So my PhD student Vivek noted this problem and decided that the virtual stigmology couldn't really deal with large data. And here you see him as a model for in a poster in Frontal Polytechnique. And since he realized that he had no prospects as a mask model, he investigated the subject and realized that the real world requires this large data transfers and storage. And they designed this new system that we called SOUL, Swarm-Oriented Upload of Large Data. Terrible name, but SOUL stores this data on different robots. So the idea is that when you have information that is too big, you just chop it into pieces and you distribute among a bunch of robots. And this idea, this very simple idea, which is something we saw in servers and other applications, has some very powerful applications in robotics. In particular, if you consider that SOUL can adapt to a dynamic and changing network, which is something that is not done in normal cloud computing, for example. So imagine that you have a disaster response scenario and you have a robot that collects information, makes a nice map of a place where there was an earthquake, like you see this little picture here, and takes this information and puts it what we call a data blob. This data blob is too big. The map is too big, so it needs to be split and distributed. So what we do is we split it into chunks, into blocks, and then we need to distribute it. But we don't have a central intelligence or a central way of deciding how to distribute these things. Therefore, we make an auction. And so we say, oh, there's data available. And all the other robots in the network submit bids. They say, okay, yeah, I can take this piece of data. I can take this out. And then we transfer this information. And then we can spread all the information across the network. When the information is needed, we do the reverse process. We request it, and all the robots that had the information send it back, we combine them, and we put them again together. This has very, very powerful applications. And this is one that I really like is, you see this very dark, unfortunately, video, where you have robots just doing some random tasks. They are going around and they have a time, a sort of function depends on time that changes the color of the LEDs. They're going around until one robot needs to go recharge its batteries. Then what they do, it completely backs up its own soul, its own computing system, distributes this backup in the other or to the other robots, and then a new robot can join in with exactly the same state as the other one. So you can back up robots on the fly and replace them. This might be important, for example, in disaster response. Another thing that you can do is when you have specialized robots. In this case, we have one robot that has a powerful processor that can do some information image processing. And we have a robot that has a camera, but it doesn't have enough processing power to detect objects. So what it does, it takes pictures and sends them through the network to the processing robot, who then detects images. For example, here we see a mouse, and then feeds the information back to the originating robot. All these things are possible through the network in completely dynamic way. So you can change the number of robots, change the number of processors, of detectors, and it would still completely work. So we developed this language and this data sharing system, and the entire idea of consensus is what we use to build larger and more practical applications. we have that this agreement that we described is really the key for our coordination, because it allows not only, as we said before, task allocation, who does what, but also allows for synchronization, it allows the storage of information, etc. And as we said, this requires the robots to communicate. What we can do with this is we define an entire design flow based on consensus. Now that we have this system, we worked, and this was mostly the work by former postdoc David Santonge, who is now a professor at ETS, to define a way to design systems with the consensus in mind. One simple example is what we call the barrier, which means we wait for others before doing things. What you see here, we have an example as where the robots are taking off at the same time. We don't coordinate, we don't send a command to take off at the same time to the robots. The robots, you see, they stop and they wait before moving simultaneously. And you will see in a few seconds, they will land simultaneously. All these decisions are made autonomously by the robots. So by exchanging information, they try to agree on the time to land, or the time to move, or the time to take off. This is a sort of AI democracy, where the robots see what each other are doing. And imagine humans, like we can look at each other and maybe say a word, and then you start walking or stop walking. Same thing. And this allows for complex coordinated behavior. One other example that I have is the task allocation. Here we have a bunch of robots. This video was taken by another flying robot. So this is the football field of the University of Montreal. And we have the robots that decide to assign a task. So they are assigned a location, and the robots are, as a swarm, are given the entire list of locations that they have to cover. And then they talk to each other and they decide who does what. And in the end, we are forming a sort of Y symbol on the ground. And the robots here are tiny because they are far away, but you can see that they form this, this particular figure. Once we have this task allocation and this ability to have structured behavior, we can step up a notch and perform what we call collaborative transport. Here we have robots that have very simple sensors. You see, they're trying to find the end of the box. They're very simple infrared sensors. They don't have cameras, but the box is too heavy to be carried by a single robot. And the robots so agree, and they end up working together to transport the object. So this type of collaborative transport is possible only if you have consensus of who does what. You see in this particular video, we have that one robot stays in front and sort of guides the other robots without, is not helping in pushing, but it's sort of guiding the entire transport. If you suppose you had to go in the opposite direction, that robot would have to push. And so the role changes depending on the situation. This also extends to larger objects. Unfortunately, we didn't have 50 robots to do the experiment, so we relied on simulation. But as you can see, the robots are agreeing on who goes next to sort of cage the object for transport. And once they have this sort of agreement and they cage the object, they can move around and even form interesting trajectories, like a zigzag motion like you see here. We can also step it up another notch and go to flexible material. What you see here is 4 robots that are carrying a fabric that is too heavy for a single robot to carry. And they are working together to carry this material. This material is complicated because it's elastic, it moves, it's flexible. So there has to be fine control of the distances between the robots. And yet this we can do. So again, another application of consensus and barriers that lead us to closer to practical applications. So far, however, you've only seen experiments in the lab. How do we take this out to the real world? Well, there are a few items that needs to be checked. First of all, we have localization. How do robots understand where they are? This is a key point. This is a part of the robot perception. The robot has to know what's what and what's where. And this is a huge problem on its own. And just for single robots, extending it to real swarms, it's even more complicated. So we did some work in this area with what we call simultaneous localization and mapping, where a robot goes in an unknown environment and looks around and maps the environments to understand what's around it, and also finds its location in this new and unknown environment. We use vision in particular, and the robots collaborate with each other to improve their localization and mapping. In particular, we collaborate to eliminate what we call perceptual aliasing. What is it? It's the effect of the hospital corridors. They all look the same. You can easily get lost because you have no real understanding of the fine differences. This is true also for robots. If you take the corridors at Polytechnique, they have all doors, they all the same color, they have the same structure. It's really hard to determine if you've been in some place before. Robots can collaborate to solve this problem. This is PhD work by student Pierre-Yves Lajoie, and in collaboration with the work we've done, it was in collaboration with the lab at MIT with Professor Carlone. So this is what you see: stereo visual odometry, distributed loop closure detection. All these big words are to say that the robots exchange information when they meet, and they tell each other the places that they have seen. And if there is a match between the places that they have seen, they can sort of discuss and fix their maps. Imagine that I see the same corridor twice and I think it's a different corridor. I see another robot that tells me this information is this is actually the same corridor. I can adjust my mental map and have a better overall localization. And we do this by, as we call, eliminating outliers. Outliers are these spurious measurements that we have that can confuse the robot. What happens, in fact, is that when you have measurements, spurious measurements in your trajectories, your trajectories end up being all garbled, so you don't understand where you actually were. So what we did was we let the robots roam around freely, but then whenever they meet, they exchange information, and they can optimize, say, the trajectory and better understand the map. Here you have a nice example that was in collaboration with MIT and NASA JPL, where we look at the maps that were formed without outlier rejection. You see the map of this mine that the robots was exploring is completely garbled, but it can be reasonably fixed when we remove these outliers, and it becomes a much neater, much clearer map that the robot can use. So there's another key ingredient for real swarms. We have that robots now are able to localize themselves. They can talk to each other, they can coordinate, but how do we operate these systems? As we explained before, we need an operator. An operator is necessary because you have to relay data back to the operator. Otherwise, it makes no sense unless the robot interacts with, like, drags people out of the disaster area. It still needs to drag these people to somewhere like a hospital. So they need to have a sort of interaction with us humans. So with that assumption, we say that robots need to establish and maintain this sort of communication with the operator. And this communication can be intermittent, so it can be disappearing, doing their thing, and then coming back to talk to us. This happens regularly with space missions. We have that when a satellite is out of communication range, it can talk to us, but it can still perform its operation. So in case of disaster response, we are more interested in what we call end-to-end communication, so maintaining communication at all times with our robots. The reason is that we want to see what is going on and perhaps interact with the system and provide additional instruction. This is again work by student Vivek. And how does it work in practice? Imagine that you have a bunch of robots. Some of these robots are free. They don't have any particular task at the moment. One robot, which we call the root, is the one that's talking to the operator. This robot could be the operator themselves. It could be simply a communication device, which is on the operator's laptop, for example. So this robot tells, hey, dear worker, go and take a picture in this area. And the robot has to follow a certain path to get to this area. This path could be complicated, it could be obstacles. For example, if you explore a cave, it could be snaking around to trying to find the end of the cave. What happens is that the worker moves on, and at some point is about to lose communication link with the root. It can tell this by looking at its signal strength, for example, for a Wi-Fi. What it does in this case, it calls for help. It says, hey, can anybody come and help me? And one of the robots that was not doing much becomes a networker, so acts as a relay between the worker and the root. Then the worker moves on and calls other relays. And in the end, you can get to the final destination and perform the task, for example, taking a picture at the end of the cave, and relay this information back to the root. You can imagine that this is kind of dangerous, because if one of these robots fails, you break the communication link. So you can also have multiple communication links. So you can ask more networkers for the level of redundancy that you find acceptable for your particular application. This is extremely useful for disaster response. You want to go in a crashed building without losing communication, and you will still want to see what's going on. You send your chain of robots into the environment. You want to explore caves, similar thing. So what does it look in real life? Well, we did some experiments in the lab with this, and also on the field. And here you see a set of flying robots that, first of all, they agree who is the root. And then they assign a worker just by election, again, AI democracy, and they plan a path to go to this particular area. In this case, the path, the path is virtual. These flying robots clearly can go above these structures, but we force them to show that they can actually follow a certain trajectory. And they get to this point where, for example, ground robots cannot fly. Here you have a net, which one hole, and the robot has to pass through it to get to the destination. And what happens is that they start going around. This is actually in real time. You see also Vivek here in the corner, happily looking at these robots. The robots form a chain, and as more robots are needed, they take off and they join the chain. You see now we have a chain that is formed by multiple robots that are all going. We have 4 networkers, a root, and a target. And they have reached the target, and then they land. This is just an experiment. We've done the same thing with bigger drones on the outside. It's not very fun to see because it basically form a line. We didn't have any very structured environment, but we are going to run these experiments also in caves in the near future. Another ingredient related to the control is the human swarm interaction. When you have this set of robots, and you have many, you have 6 in this case, but you could have 30, you could have 50, 100. How do we get what we call situational awareness? We have a bunch of robots that are exploring in all different directions. We don't want to have the operator go crazy trying to follow each of them. So we started studying human swarm interaction, and we have several collaborations in the area with the University of Modena, Reggio Emilia. We have collaborations with NASA JPL. We have collaborations with ETS and Concordia. The idea here is that I present just a small subset, which is the PhD work by student Marcel Kaufmann in collaboration with NASA JPL. So how do we do this? Well, first of all, we have to find a good way of measuring cognitive load. Cognitive load can be measured in many different ways. We are not experts in psychology, or so we rely on our collaborators for this. But I can tell you that this can be measured by either checking the pupil size or the skin conductance, so electrical properties of your skin to detect how stressed you are, or the variation on your heartbeat. And all this information can be collected and used to check if the operator is freaking out or not. In particular, Marcel worked with NASA JPL to create a copilot. And this copilot is a sort of an AI that sits with you and provides a user interface and helps you schedule your activities to control a large swarm, provides prioritization of tasks, provides alarms, reminders, and what we want to have, JPL still doesn't use it yet, but what we want to have is biosignals to monitor cognitive load. We have run several experiments, as I will show you in a minute, where we actually measure the cognitive load, and we are capable of detecting if the subject is going to saturate. And anyway, JPL used this copilot system to explore caves with their fancy legged robots. So overall, we have this nice collection of algorithms and software to help interact with a large swarm of robots. I have a bonus here that is not entirely related to the control by the operator, but it's more related to common people. What we have here for JPL, for astronauts, for first responders, we will have highly trained personnel interacting with the system. So the system can be complicated as long as it doesn't exceed the capacity of the operator. But what if we want to have the common people, if we want to have Plumber Joe interact with the swarm of robots? We studied this idea together with Dr. Santonge at ETS, and we looked at how swarms of robots can provide moods and information by motion. So the idea is that, can we have the robots express something with their motion? And we took this to an interesting level, thanks to Dr. Santonge. We took it to artistic performance. So we had robots dance with some dancers at the School of Dance at the UCAM. And what we ended up having is that the dancer expresses some feelings with the dance, and the robots react accordingly. We do this with by measuring the accelerations on the arms and legs of the subject and classifying the moods of the dance. And you can see we have a coordinated performance between the dancer and the robot. This was an interesting experiment that shows you that even for artistic expression, we can use swarms of robots. What is the last ingredient that we need for real swarms? And this is what we call long-term autonomy. We want to have robots that we deploy in the real world and they keep working. They don't have to go there every 5 minutes to change their batteries. We want to be able to update their software while they're out. We want to be able to need to collect them and put them all together to fix them. So we did some work in this area in order to be able to deploy and maintain swarms of robots. The first thing we've done was what we call continuous software integration, meaning updates. you do updates regularly on your phones. And this is done in a sort of centralized way where there's a central server that distributes these updates. This might not be the case in disaster response. We might not have a communication infrastructure. The environment might change. Some robots might not be in communication range, and you also have time constraints. If you want to do it in a rush, you have to solve the problem and do it quickly. So traditionally, what people do with robots is that they fly the robots, they move the robots, then they put them down, they turn them off, they plug them into a computer, they run an update, and then they redeploy. This is not acceptable if you have thousands and thousands of robots over large geographic distances. So the solution is over-the-air updates. And our idea was to send updates to one robot, and this robot then creates a new software release and broadcasts patches. And we use consensus, the same consensus that I described before, so that all the robots agree to the same software revision, and there are no issues when running the software on the whole swarm. Another problem that we have to have long-term autonomy is what we call energy sufficiency. Now we can update the software, we can have them coordinate, we can have them localize. They change, the robots generally run on batteries. So whatever mission, we have to make sure that the robots go to recharge. And to do this, we need to have a sort of way to coordinate the access to a charging station. And this is the work of PhD student Hassan, also known as the big friendly giant, who's holding it at 30-kilo rover like it's 10 grams. But his work shows us that we can indeed control the robots in such a way that no matter what the mission is, we can guarantee that they go to recharge. Here we have two examples. First one is that we have this red dot in the middle represents a simulated charging station. We have that the robots are going around randomly, and whenever they have the simulated battery to make it more realistic, well, to make it visible in real time, when their battery goes below a certain level, they go to the charging station. Interestingly, they do so in coordination. So they don't end up with the two robots trying to go to a charging station at the same time, of one robot being charged while the other is run out of battery and cannot get to the charging station. And this is done again through consensus and communication. And on a practical application, we have a battery swapping system that performs the job of the charging station. Here you have a robot flying, finding the battery charging station platform, and then I'm accelerating a bit, landing down, and then there's a mechanical arm that comes, replaces the battery with a new battery, and then the robot boots up and then takes off again. So we can apply this algorithm with our charging station. So you might ask at this point, okay, you showed us a lot of things in the lab, but did you do anything practical? Did you do anything real with these swarm missions? The question is, how real is this? And this is actually more real than you might think. We did some tests a couple of years ago already in Lanzarote in Spain. That's an island in one of the Canary Islands. We had 6 robots controlled by an astronaut, an European astronaut, Matthias Maurer, in a lunar analog exploration. So we went there with our 10 robots that you can see in the picture, and we had the astronaut control them on an exploration task. So they were trying to find features of interest, geological features of interest in an area that looks like the moon. So this is where we went. This is the volcanic island. It's very similar in terms of types of rock and structures compared to what we can find on the moon. And here you can see astronauts training for EVA activities on the moon. As you can see, it's really rocky, sharp rocks, very abrasive, like you find on the moon, for example. So we went with our team. We have PhD student Marcel, we have Benjamin and David, and also our collaborator, Professor Coffey from Concordia in the Department of Psychology, and PhD student Yanjun. We went there and we did our cognitive load measurements. Here you have Matthias Maurer wearing a pupillometer. You see the picture here. We're measuring the dilation of the pupil, and this tiny vibration of dilation of the pupil can tell us a lot about the cognitive load. Here we were calibrating by giving the astronaut a task to do in the tent, so that we would know what are the how to calibrate this pupil movement with the cognitive measurements. Then we went outside and we do the same thing. We gave him a tablet, and this tablet allowed the control of 6 robots. And you could also look at the robots to see what they were doing in real time. And we had these nice 6 robots flying. And this is what they look like in real life. Unfortunately, being the distance involved, except for takeoff and landing, they're really hard to see because they can be up to a kilometer away. So that's why it's very important to have this tablet interface to control where the robots are going. Here we have another person trying the system. So we did some pretty convincing real experiments, and everything that we've done use the same consensus, task allocation, communication, and data sharing that I presented before. We have more missions coming up. This July, if the pandemic allows, we'll be on top of Mount Pilatus in Switzerland. And with this theme, we'll have no more flying robots. We'll have rovers with advanced sensors. And these rovers will be controlled by a single operator. We also have the RoboDog to explore an environment. And in particular, we will have this area, which is about 100 by 200 meters with large boulders, rocks, and uneven terrain. And the robots will start from a tent. They will have their own charging pad so that you can also test our energy sufficiency algorithm. They will have a base, which is an hour and a half away by train plus car in the Museum of Transportation in Lucerne, in Switzerland, and the operator will have a simulated delay and communication bandwidth with the moon. And the operator will have to recover a map and find some little aliens that we had distributed around the environment, just to add some additional challenge to the operator. So this is coming up in a couple of months. We will also do a dry run of this experiment at the Canadian Space Agency Mars Yard in May. We also have a plan for future missions, and these future missions are the moon and beyond. So this is a mission that we actually proposed to the European Space Agency, to have multi-robot exploration of lava tubes on the moon. And we do this with spherical robots. I haven't talked about the mechanical part of our work where we designed flexible robots, or in this case, this is a collaboration with ETS where they designed spherical robots that are robust, agile, can jump, and they can form a local network with connectivity maintenance with a rover. They can recharge with a charger and perform the mapping of the cave fully autonomously, with very low mass, and with this capability of exploring the environment, acting as a whole swarm. That being said, with this grand view for the future, I would like to conclude saying that swarm robotics is coming in the real life, today, in what we see and feel and explore every day. And we need new technologies and new methodologies to define the behavior of these large groups of robots, especially as the behaviors become more and more complex. The more complex they become, the more we have to rely on what we call emergence, which is the fact that many stupid things acting together can be like a smart organism, like our single neurons, for example. And consensus is the key to coordinate this group behavior. And our language buzz can actually help engineer effective swarm systems. All this that I presented wouldn't have been possible without the support of many, many, many students and collaborators. So I would like to thank them all for the help, and the funding agency for the support. So we got collaborations in particular with the CLASP laboratory at Concordia, the INIT lab at ETS, and the Spark lab at MIT. We were supported by CSA, NSERC, JPL, FIQNT, NFRF, and also companies like Speary and R, and many others that no space to mention in this page. Anyway, thank you for your attention. I'm open to questions.
Yeah, thank you very much, Giovanni, for this really impressive presentation of applications of autonomous robots. We have a couple of questions already in the Q&A. So I can take the first one. So I think it's just a practical question. I guess you showed a couple of times. So for example, the drones on the football field. So we have the questions. So what decides when to take off or land? Is it the operator, for example, or? So
this can be either a scripted mission, like when you achieve a certain objective, you land. When you're out of batteries, you land. Normally, there's an operator. We made for that particular experiments, we had a graphical user interface with the land button. And if the robots are below a certain level of battery, they automatically come back to a home spot, and they land. So this, again, can be scripted and depends on the application.
Okay, thank you.
Thank you so much, Professor Bertrami. We have a question. So how do you imagine that the first commercially available robot swarms? Do you use optimization-based methods during the design of the control software of the robots?
Commercially available, very soon, very soon. We're working with companies, in particularly Spear Robotics. We're working with them to have a commercial application on the field. One of the applications we have is to, actually, I don't know if I can say it, so I will not, but we have commercial applications coming up, and the idea is that there is optimization involved. So this the entire concept of task allocation is an optimization process. So we do optimize the single controllers of the robots, but we also want to optimize the behavior of the whole swarm.
Thank you so much.
We have another question on YouTube this time. So first, a comment from the attendee that the Sol is really cool. So that you can see that how it can benefit a lot of applications. And then in terms of consensus, however, would you say that it's still challenging for the swarm to reach a global consensus on big data?
Well, the idea is that the more bandwidth you need, the harder it is. So one thing we're working on is, imagine that you have to do continuous learning. And you have a lot of data that you need to share, because if you want to learn, you need to have the data set. Google is already doing it with federated learning, where you have each device learning on its own, and then they talk to a centralized server to get all the models together, and then to distribute them. You can do the same thing in a fully distributed way. So you can have the robots use consensus on the model weights. And so you can do learning without the robots they never have access to the full data set. So you can have consensus on the learned product without having to share everything. So there are ways in which you can go around this problem of sharing large data sets.
Thank you. Another question. What technical challenges do you foresee that you will have to deal with in the future, especially in terms of tackling behavioral emergence?
This is an excellent question. So we still don't have the answer to this. We are working on it. And one of the technical challenges is that it's due to let's say the structure of nature itself. We have that chaos, unpredictability, and self-organization are intimately linked. So the same things that cause the unpredictability in the universe, like chaos theory, are what gives us patterns, gives us structure, like the morphogenesis, the formation of our own organs, and how the embryo develops is due to the same kind of behaviors. So what is difficult for engineering these systems is how to structure and abstract in such a way that you can sort of have a hierarchy of different swarm behaviors that you can compose. This is extremely difficult. We are working now, Vivek, in fact, is working very hard on how to run an experiment where we have a sort of hierarchy of swarms, a swarm at a higher level controlling a swarm at a lower level. This is the main technical challenge if you want to engineer something that really uses emergence to perform a behavior.
Okay, thank you. So another question from the attendees. For example, during, I guess, mission where when there are humans involved, how can the robot sense hazardous conditions to their target use?
So yes, that's a good question. Thank you. The robots have perception. Perception is generally studied as for single robots. Having multi-role perception is something that is reasonably new. The idea is that we have sensors, and I have another student, David, who's working on detecting exactly problems and issues. And imagine that we have a project where we're looking, for example, at a robotic kitchen, and things can fail in the robotic kitchen, and we want to detect when this is going to happen before it causes too much damage, and we want to alert the operator of problems. So fundamentally, we use machine learning. We look at the environment, and we try to detect anomalies. Whenever there's something anomalous, we present it to the operator, and if it is recognized as a particular type of fault, for example, there's a cliff, or the floor is slippery, or there's radiation. This can be communicated directly to the operator at a different priority level, depending on the gravity of the problem.
Thank you. Another question from attendees. How is the decision-making actually happening in the task allocation collective movement scenarios? It's more about the assignment of roles.
The task allocation happens, we use not really novel algorithm. We use what we call market-based allocation. So we use auctions. Robots are saying, okay, I want to do this task, and I bid X. And the bid depends on the type of robot, on the battery level, on the position, on the type of task. So we calculate this formula, and the winning robot, the robot with the highest bid, let's say, wins the task. And if you have a tie, we also have a way to avoid conflicts. So to resolve conflicts. This could be just a robot ID saying the robot with the higher ID wins. Could be anything else. The idea is that there are rules that you can use to resolve conflicts. So in the end, it's a round of talking and checking the bids, talking and checking the bids. This assumes that the robots are all cooperative. You could have malicious influence. And this is another problem that we addressed of adversarial conditions. And we did some work in collaboration with the University of Cambridge with Dr. Prorok, where we looked in this adversarial conditions, how we can hide, let's say, the information from the swarm. Hide who got the task, for example, or we can, there are also algorithms that allow to certain message passing strategies and way to structure the topologies to avoid these adversarial conditions and filter them out.
Thank you. Great. Do you have another question, Fabian?
No, I think there are no other questions in the Q&A.
I have a question. So are there currently any regulations that limit the use of these technologies in a real environment?
For flying robots, yes. Transport Canada has very strict regulations. There's no real, in fact, you cannot, at the moment, without a special permit, fly drones in general. You need a license. And you definitely cannot fly a swarm of robots with a single operator. We do have what is called a special flight operation certificate that allows us to fly the robots for experimental reasons, but excuse me, a company would need to obtain such permission at the moment. But regulation is changing. We'll see. For the other robots, the usual safety industrial standards that apply.
And according to you, which industries are most interested in this kind of technologies?
There's a lot of potential in logistics, transportation, air traffic management. This is really the key point. That I would say the logistics is one of the ones that will be impacted first, but we also have construction. If you can automate, you have robots doing different tasks. Construction is very complicated. You need lots of different tools, lots of different specializations. But if you can have robots doing different things and working together, that will be an impact. But it will be later in the future. I think the first one will be self-driving cars. Well, let's say logistics first, then self-driving cars, and then construction. This is how I would say, but speculation.
That's perfect. Thank you so much.
I may have one question on my side to end the Q&A session. I guess you already kind of addressed this question at the end of your presentation, but now, so recently we saw that there is a new rover that landed on Mars, so Perseverance. And do you think that in the future we can see kind of like swarms of, for example, of drones with the rover on the ground in the future?
Yes, definitely. This is in fact the plan by NASA. They already had a few studies where they called the Mars bees, where they had the small flying robots that are deployed by a rover. This is similar to what we proposed for the moon for ESA, and it's the way to go. The idea is that if you have a single rover, no matter what you do, they will be able only to carry a certain travel distance during a day. They can only be able to explore a limited amount. If you have 10 flying robots, you can explore 10 times and from the sky. So you can imagine you have this rover that deploys a bunch of robots. They look around and they find the best place where the rover has to go to perform its science exploration.
So, yeah, so looking forward to see that in the future, I guess, in the coming years.
We will.
Okay, so again, thank you again, Giovanni, for this really interesting presentation and discussion. And thank you to all of the attendees for participating in this webinar. And so we wish you a really good day and hope to see you soon for our next webinar.
Thank you. Have a nice day.
Thank you so much.